So our speaker today is Albert Lazzarini. Albert is the head of data and computing for LIGO, which really means he's in charge of all the data analysis for LIGO, and he's the boss of anybody who thinks about data analysis. So I think about data analysis part of the time. I guess he's my boss part of the time. Albert.
Thank you. Good afternoon. Kip had asked me to put together a lecture for your class on what we're doing at LIGO for planning for the LIGO 1 science run and possibly talk about LIGO 2. The emphasis I'm going to place today will be on apologize. The emphasis I've placed today will be on the LIGO 1 activities that we're pursuing. And I was going to organize this lecture to briefly remind those of you who may not be aware of it of exactly what LIGO data attributes might be. I was going to provide a summary of noise processes, how we deal with random data, their time and frequency domain properties. Then I was going to show how all the gravitational wave signals that we might think about can be fit together in a time-frequency classification from chirps to bursts, and how that suggests a strategy for going after different types of sources. Then I was going to mention search techniques for specific classes. The time will not permit to go through exhaustive discussion of all the sources, so I picked the in-spiral and chirp as a classic paradigm for how we want to do optimal Wiener filtering. And I also then will discuss briefly how we do much more unmodeled time-frequency domain searches, where we basically look for glitches that are unexpected in the historical trend of the data. As appropriate, I'll mention computational cost and implementation, how we're going to go about taking the ideal situation that's been described in numerous papers and how we implement that in software to try to do this on a continuous basis with our large data volumes that we have. And then I'll touch briefly on the strategy that we are planning to take advantage of the fact that LIGO is in fact building 3 detectors, not 1, or 3 interferometers that constitute 1 detector that will be used in a coherent manner, and that there are other detectors around the world that are coming online about the same time, and we're already starting to formulate agreements with other international programs to look at formulating how one might put together an international network or phased array of gravitational wave detectors. As a reminder, you've had several lectures discussing interferometry and their application to the problem at hand, that we have a limiting noise curve that is dominated by 3 different, we have a stick? Thank you. Thank you, Kip. At the lowest frequencies, we're limited by the fact that we're living in a terrestrial environment and the Earth is a moving body. In the mid-range, we will be dominated by the fact that we're operating at 300 degrees Kelvin, so we have a thermal noise component where the materials of which our systems are made, the mirrors, the fibers, are always in thermal motion and produce, at least for our case, an irreducible thermal noise source that will limit the mid-range of frequencies. And then at the highest frequencies, we're limited by the fact that we sample for progressively smaller and smaller periods of time to make statements about sensitivities at higher frequencies, and so we're limited by how many photons we can collect in shot noise. The sensitive region, as you know, then, is this U-shaped area that kisses something like 10 to the minus 23 in spectral density per root hertz, as we use to quote the sensitivity of our instrument. And I should mention that this curve is representative of what was written in the 1989 proposal all of 13 years ago now, and subsequent insights in the properties of thermal noise have rendered the details here slightly changed, but we still use this as our target sensitivity curve for LIGO 1 system. And the other point is that lurking below the sensitivity, indicative of a system that's been optimized for a particular targeted sensitivity floor, is that there are other components of thermal of noise that will come into play as we produce progressively better instruments. And so we have to manage the thermal noise, the total noise budget in a systems level sense to produce advanced interferometers that expand the sensitivity region in all directions. I picked out two representative graphics from the literature that then attempt to place on the sensitivity curves for various generations of instruments, and the focus for my discussion today is the blue curve here, which is LIGO 1, and the top dark curve labeled initial LIGO here. And this shows if you ascribe the change in the period of the millisecond pulsars that have been measured to the emission of gravitational waves, and in some sense you can put an upper limit to the strain signature you would expect if you could account for the slowdown of these pulsars due to emission of gravitational waves and quadrupolar formalism. And over here I took a set of composites that Kip had produced for an initial advanced LIGO conceptual design that we put together 2 years ago, in which he had done a really good job of compiling on here all the different types of sources, from the stochastic background to the trajectory of the chirps as they come through the band, to potential sources of gravitational waves from pulsars, which are also replicated here. The bottom line is that we will be expected to be operating at the very limits of sensitivity for our instruments. Until we get to the more advanced interferometers, we will be working right in the mud, so to speak, in terms of what the signal that we obtain from the instruments is and what we try to extract from them to make statements about astrophysics. Consequently, part of the design of the instrument is to recognize that we have built a very sensitive transducer, this interferometer, which unfortunately is not sensitive only to gravitational waves. It has a response to Earth motion, to laser light amplitude and frequency fluctuations of the light source, thermal noise, as I mentioned, and because we have small miniature magnets that are used to control the attitude of the mirrors and their axial position to keep the system in lock, we potentially have some concern about being sensitive to electromagnetic interference in the ambient environment. The consequence of that is that we have provided for a design that acquires many channels beyond just the gravitational wave channel. We look at signals that are reflective not only of the differential motion, which we map into the gravitational wave strain, but also the common mode motion, which carries information about laser frequency fluctuations and alignment errors. We have an array of microphones to look for ambient noise effects that could couple acoustically through pressure waves back into the transducer, into the interferometer. And we have seismometers that look for ground motion to be able to determine whether there's excess motion in the interferometer, that could be explained by excess ground motion during a particular epoch of data taking. In order to keep track of all these multitude of signals that we collect, we formulated jointly with the European Virgo program a frame format standard for how we will acquire data. And we've worked very hard over the past 4 or 5 years to make sure that what we write here in the United States can be transparently analyzed by the Europeans and vice versa, and that's a significant fraction of our software development efforts, is to guarantee that we have interoperability of the software. We want to eventually exchange data, as I mentioned, but more importantly, at some point that provides us with a measure of independent software development activities that look for the same signals in the data. One interesting fact is that we acquire the strain channel at 16 kilobytes per second, 2-byte digitized integers, so we have something like 30 kilobytes per second as the data stream that we acquire from each of the 3 interferometers. Dwarfing the 32 kilobyte per second data rate is a 2 megabyte per second data rate that corresponds to the rest of the servo systems that are collected in the interferometer, which are basically health status and housekeeping signals that will be used to verify that what we see here is credible for the epoch in which a putative event is detected. The environmental sensors that I mentioned earlier, the magnetometers and seismometers, correspond to yet another megabyte per second of environmental data that we acquire. So when you put it all together, The science channel, where all the physics, astrophysics will be contained, is approximately only 1% of the data that we acquire. And we use GPS timestamps to provide up to levels of about 100 nanoseconds exact timing in the data that we acquire at both of our LIGO sites. So, in summary, we collect 1% is the gravitational wave channel, and I think I've already mentioned most of these things, so I can pass a slide. We are worried about, for example, whether you have line spikes. Everything is nurtured by the 60 hertz power grid in the Northwest or in Louisiana, so we are always monitoring the 60 hertz signal to see if there's potential for transient pickup into our interferometers. The accelerometers provide for high-frequency shock and vibration measurements at frequencies above about 100 hertz. Magnetic fields are of concern, so we have magnetometers that look for time-dependent fields such as those that might occur in a building if you turn motors on and off. You've got the wiring network of the building, which then, in the presence of this transient, produces a time-dependent burst of signal that could, in principle, couple to the interferometer. Seismometers provide for low-frequency ground motion, and I've already mentioned acoustics. One concern we have is that we have 4-kilometer tubes that are highly evacuated, but if at any point gas outgassing bursts occur within the tube walls, they could, in principle, produce a phase fluctuation that looks like a burst in the interferometer, and so one actually monitors at some low sample rate, but with the ability to trigger when events occur, substantial changes in vacuum pressure. And the Oregon group, in our collaboration coming from high energy physics, has actually instrumented a muon shower detector, which we're looking for site-wide cosmic ray showers that could illuminate the LIGO interferometers. It's been shown that such high energy showers are detectable in cryogenic bars, and so we want to also ask the question whether there was any external cosmic ray activity at the time of any transient phenomenon that may be observed. How will we use these channels? Well, one thing we want to do with those channels that have the highest signal to noise is to potentially cross-correlate and remove the contribution they make to the strain channel by a linear regression analysis, a standard least squares fit comparing a matrix response of many channels to one channel. The other purpose of the multiple channels is to validate that if we see something in the H of T channel, that the instrument was behaving nominally. So we want to continuously monitor interferometer environment and make sure that all these signals are within nominal, let's say plus minus 3 sigma performance. The other thing we can do is, empirically, we can determine what a typical channel's power spectrum looks like, so that we can actually compare the data at this epoch with historical trends to identify whether we have any outliers in the behavior of the instrument. Another interesting thing that we anticipate wanting to do is to actually have an empirically determined template bank of instrumental glitches that can be used just as we would within spiral templates to detect and to veto for things that we know are happening in the instrument. And if time permits, I'll go into that briefly. And the last thing is we're in a position then to veto when data are clearly out of the normal behavior due to the ambient man-made environment at our sites. A good point to anchor our discussion then is to ask how well we're doing to date and where we plan on going with the interferometers. And you may have seen this in earlier lectures. This is a composite of the 3 interferometers operating during a 3-week period, 2.5-week period over the holidays, when we had a very intense data taking session that we called the Engineering Run 7. And overall, I show on here where the LIGO 1 science requirements document goal is. So we see we have a ways to go, but we also have a vigorous commissioning and research program that's being undertaken by the laboratory and the collaboration to try to push these experimental curves much closer to the target. One thing that should be mentioned is that this particular run was taken at very low laser power. So at least at high frequencies where we already have the trend that's parallel to the shot noise curve, these curves will be expected to drop by the square root of the 1,000 difference between this power and the design 10 watts. So we anticipate a quote-unquote automatic factor of 30 improvement as we go to full power. And the other thing is that the electronics at high frequencies are designed for the full power configuration. So when operating at reduced laser power, you have a larger contribution of electronic noise that will also diminish as we go to higher power. So the expectation is that the curves at the high frequencies will come down and approach, as expected, the sensitivity of the design sensitivity. It's interesting that we have what appears to be a 1 over f cubed limiting noise in the low frequency, and that's currently clearly instrumental in nature, not intrinsically related to the seismic wall that is expected to produce this limit. And that's currently an active area of investigation by the commissioning team to understand what's the cause of this 1 over f cubed noise behavior at low frequencies. In several places in several of the subsystems associated with the interferometers, we already know that the electronics need to be upgraded to produce greater sensitivity for those servos that are most sensitive to contributing to the ultimate design performance of the interferometer. That's currently something that's being done by the electronics group in the laboratory. Some of the structure around 200 hertz is related to known mechanical resonances on the optics tables where the laser light originates that is being driven by seismic excitation at both Hanford and Livingston. So there's got to be some redesign of out-of-vacuum components to limit their pickup of the seismic environment and their amplification of the environment through these structural resonances in mechanical systems. And the last important thing is, before we go into a full science run next year, we want to upgrade the seismic isolation system at Livingston, because we have found that historically we have much greater ground noise motion that depends on the time of day at Livingston than was originally anticipated in the design of LIGO, and so that's an upgrade that has to be performed before we can approach, for the Livingston interferometer, the sensitivity curve of the design. So the battle is noise versus signal, and unless nature is extremely serendipitous, we expect that we're going to have to work very hard to sift through the interferometer data to look for putative events with the initial interferometers. So what does that mean to us? It means that if you look at the signals that might be there, we're looking at integrated signal-to-noise ratios of 10, which is considered at the margin of detectability. But that means, since many of our signals, such as chirps, have extended duration in time, if you look at the time domain data series that are being acquired, the instantaneous dynamic signal-to-noise in any one slice of time taken at 16,384 samples per second is going to be many orders of magnitude below the integrated signal-to-noise for the entire signal. And this is nothing new. This is very much the domain, for example, that astronomers have to deal with when they're looking for pulsars. You have to integrate large epochs of data before you can pull a narrow feature out of the noise floor of the radio antenna. And our focus for the foreseeable future will be in trying to understand and reduce sources of noise. We want to continue to do instrumental improvements, as I've suggested we're doing now, which allow us to control the noise prior to the point where it's acquired and digitized, at which point, once it goes on tape, we're going to be left to the devices of our cleverness with regard to signal processing techniques to do whatever cleanup we can after the instrument has done its best to produce a good sensitive signal. And the analysis strategy that will be exploited for LIGO is then doing hypothesis testing on events that we see to assess whether what the confidence is that an event may be present versus an event may not be present if we're operating in these really low signal-to-noise regimes. I was going to now provide a brief reminder or overview for those of you who've seen it before on how we deal with random noise processes in either the time domain or frequency domain. If we have a noise signal that's randomly varying with time, so at every epoch you have a value for the measured parameter that is statistically random, if you histogram or produce a projection of the number of times a particular value for your voltage, let's say out of your transducer, is measured, what you will get is that the histogram manifests itself as a Gaussian process in the probability distribution function on how often you measure a value n for a parameter that's distributed about a mean mu with a variance sigma squared. And one can typically remove the variance, the mean from the process without loss of generality. So typically one worries about processes for which you have zero mean and unit or normalized standard deviation for sigma squared. Then typically what one wants to ask is, if you observe this process over a long period of time, what is its average in the time domain, which then is taken as the limit over the integral over time as the limits of the integral approach plus and minus infinity. The other question you might ask is, if I had many different interferometers all operating at the same time, what is the ensemble average of the process, which then is not the average over time, but the average over the probability density function that n is observed of the process. And there are certain properties that are assumed implicitly in many of the analyses that are done just to make them tractable. One is that the statistical descriptors of the process are stationary in time. In principle, you can relax this, but typically you assume that mu and sigma do not depend on time in many of the analyses that are performed. A very important one is what's called ergodicity, which is that if you do an average over many different realizations of the noise process, it's equivalent to doing an average of one noise process over a long period of time. In other words, that if you look at one channel and wait long enough, it will sample the phase space that's representative by the probability distribution function, the same way that if you had n such samples being observed at the same time for any one instant in time. It's crucial because all we have is one data stream. We don't have a large number of interferometers, at least not yet. So doing any type of averaging involves doing a time average, but many of the statistical inferences that are made assumes that you've done an ensemble average over the population. We go back and forth between the time domain and frequency domain for many of our analyses, and the reason for this is that computationally many equivalent analyses are performed more efficiently in the frequency domain. And I remind you then that if you have a process x of t, if you integrate over all time for multiplying by an exponential that then produces a frequency-dependent phase shift e to the minus 2 pi I ft, this produces formally the frequency representation of the signal, which I term x cap of f. And these are inverse transforms of each other, so that I can go back and forth between time and frequency by simply changing the sign of the complex weighting function, the exponential. And the processes produce a unit, have an identity function, which is the inverse operating on the function, produces a delta function in time, which is equal to the exponential of the difference in time of e to the minus 2 pi I f. And this is normalized to provide unit area under the delta function. Computationally, you don't deal with continuous time processes, so you have a digitization process that produces discrete quantities. And to a suitable approximation, then each of these integrals can be represented as sums for fixed time steps that then correspond to discrete time Fourier transforms of the process. And these have the exact same corresponding behaviors that I discussed earlier with regard to the frequency domain. The cost computationally that it takes to go from a series of data points that were acquired by an instrument of length n to their frequency representation is something like 5 times the number of points times the log base 2 of the number of points for the fast Fourier transform, which is the most efficient method by which you can produce this representation in the frequency domain from the data. To give you an idea, if I had something like 20 minutes of data, 15 to 20 minutes of data sampled at the LIGO sample rate, we have to do something like 2 times 10 to the 9th, 2 billion floating point operations from this formula to obtain this frequency series from this time series. If I have a requirement that I don't lose pace with the rate at which data are being acquired, because we're going to go into an operational mode where we operate around the clock to maximize the observational uptime of the instrument, then I have to do the 2 gigaflops, that's a typo, 2 billion operations in the unit of, oh, I'm sorry. I have to do 2 billion operations in 1,000 seconds, which corresponds to 2 million floating point operations per second. And in the jargon of computer system architectures, this is known as megaflops, million floating point operations per second. Now, if I had to do this analysis on, for example, on 20,000 channels, if I were acquiring 20,000 channels and I was asking for their frequency representation all at the same time, this then would be multiplied by 20,000, which starts to take us into billions of floating point operations per second, 40 gigaflops, which implies that the architectures that we'll be using to look at LIGO data are going to be clusters of CPUs, many machines that are operating concurrently, all doing this part of the same job to accomplish the end goal on a reasonable time scale that we can use to do the analysis. And if you do the bookkeeping on how much Fourier transformation takes place in LIGO data analysis, going back and forth between frequency and time, we calculate that approximately over 90% of the CPU time involved is involved in doing these types of Fourier transforms. So the question then is, how does this map into what I can go out and buy, and can I afford to buy what I need? And this represents, it's an Excel spreadsheet that was calculated by Kent Blackburn in our group, where he took 3 representative architectures, and unfortunately such plots become dated within a few months because the market-driven performance tendencies are very dynamic. But at least in terms of a snapshot taken approximately 6 to 8 months ago, we looked at a particular 1.2 gigahertz processor with a certain amount of memory, and we looked at the then very new P4 Intel chip of comparable speed. And then we also had a box that had 4 different CPUs that were in a parallel configuration on the same motherboard, symmetric multiprocessor machine, which is used for doing parallel vector computation. And we basically took a look at how many millions of floating point operations per second, that's megaflops here, we could accomplish on these various architectures of CPUs that might be representative of what we want to use for our analysis, as a function of how long a data stretch we wanted to analyze. So this is going from the ridiculously small of 8 points to 1,000 points, all the way out to 1,000,000 points FFTs. And we stepped through the same calculation over many, many data sets just to get a statistical understanding of what kind of performance we could achieve with such processors. And 2 things immediately stand out. Not all the computers, even though they have the same clock speed, do equally well, and this has to do with the details of how those particular chip architectures are configured with regard to supporting fast Fourier transforms. So it's important to take representative samples out of the market population of computers that you can afford to buy and do benchmarks such as these before you make a decision on what kind of architecture to buy. And the other thing you see is that you have a plateau and then a very rapid fall off as you get to the longer and longer FFTs.
It looks like you're running out of RAM.
Sorry?
It looks like in the astrophysics search codes you're running out of RAM.
Yeah, unfortunately, okay? We do very long FFTs, and so for us, we're always operating in a regime where much of the market-based commercial CPUs, such as these are representative individuals from those populations, are at a level where we're operating far below the optimum, but luckily they're very, very inexpensive compared to mainframe supercomputers, so we can still afford to do the job. But the important thing is that you can't just take the clock speed and automatically say how many CPUs I need. You have to do such an analysis as this and include an inefficiency or degradation factor associated with the fact that we're constrained to do very long FFTs for the types of analyses that we're doing. And the interesting thing is that in the mid-range where the chips perform optimally, they do approach something which the rule of thumb is that each hertz in your speed corresponds to 1 floating point operation. You can do 1 for every clock cycle. And more or less, certainly for the AMD chip, you approach 1 gigaflop for a 1.2 gigahertz processor for FFTs. Unfortunately for us, we're down at about 175 megaflops, and so we've got a factor of 8 degradation in how many chips we need, how many processors we need to do the kind of computation that we want to do astrophysically. Was there a question that I cut off?
Well, it looks like if you would add more RAM on the same motherboard, it would just...
Yeah, that's true. But the problem is it's a level 2 cache on the chip. It's not the motherboard. It's the fact of whether you can do the FFT on chip or whether you have to use the bus to get the data out of ROM.
I think it's the bus speed.
It's the bus speed, okay? And that's defined in the architecture. It doesn't change as fast as the chip speed does.
So it's not clock speed. It's not really clock speed limited.
You know, this is clock speed limited. This is our complete integrated chip on the motherboard limited. And the way you extend this out is you either go to maybe 64-bit architectures where you can do 2 steps per cycle if you're doing a 32-bit arithmetic, or if you pay a very exorbitant price, such as much of the high-end Sun, Silicon Graphics, HP supercomputing architectures, they put many megabytes of on-level cache, and that typically extends the performance. But for commercial commodity PCs that we intend to use, given the budgetary constraints we have, we can accommodate it, and we just have to be aware that there's this inefficiency factor that comes into play.
So, Albert, this comparison was not done with systems having the same motherboards, for instance?
No, you get whatever the Dell sends you. We bought 3 Dell computers. So that was a kind of an aside in terms of how computing comes back to touch on what we want to do with regard to signal processing. And one thing that is used frequently, and with the assumption that one is familiar with it, are the various formulae and identity that follow from Fourier transform arithmetic. One is Parseval's theorem, which says that if I add the power or energy in a signal by taking its square and add it over the entire time of the signal, I get the same answer if I ask what the square of the power is in the frequency domain. So this is equivalent representations of the same quantity, which is total signal power. If I have a signal that's offset in time, going through the arithmetic of the Fourier transform, it turns out that I have the exact same transform with a frequency-dependent phase shift that's introduced by the time shift t prime. We collect data with digitized ADC, so we know that the data are real numbers, which means that we can oftentimes take advantage for computational reasons, or at least and also for deducing identities when it comes to doing analytic calculations, that the frequency at f and the frequency at minus f of the Fourier transform correspond to complex conjugate pairs. And the last 2 things then is asking what a signal at a time t multiplied by a different signal at a time t plus tau looks like if I integrate that over all time. And that's called the correlation function r of tau between the channels x and y. And if you do a Fourier transform of that, you end up with a numerical estimate that can be deduced from raw data of what the power spectrum or the cross power spectrum is between the channels x and y. And there's a factor of 2 in the normalization of the definition, because these integrals extend over the full space, and for engineering reasons, Sx or Sxy has historically been assumed to be a one-sided function that goes from 0 to f, so you have to, if you integrate from 0 to f, you need to get the same power as you get from minus infinity to plus infinity. And there's always a factor of 2 that shows up when you define the power spectrum in engineering units. If you go through what the correlation coefficient looks like then, using the various identities that I showed earlier in terms of frequency domain representation of signals, what you get is that the correlation between 2 functions in time corresponds to the product of their complex conjugates of the 2 frequency representations of the signal, and that's called cross-correlation. And if I ask what the signal is correlated with itself, I get an autocorrelation function, which is basically the power in the signal that we discussed earlier, and that's called the power spectral density of the signal. And the square root of this is what's shown in the LIGO sensitivity curves that I showed earlier. If instead of taking time with the same sign, I introduce a -1, I get what's known as a convolution, where I look historically of the overlap between a function in the past and the current value of the function. And just working through the arithmetic, not surprisingly, the minus sign here manifests itself that instead of getting a complex conjugate, you simply get the product of the two frequency representations of the signals A and B. And this is typically used, for example, if you have a transfer function where you have a filter that's being processed on the data that includes the past history of that channel. Then the way you take into account the filter function in the frequency domain is a simple product of the transfer function H or B on the data A. An important property that goes back to the ergodicity, which meant that it was stationary in time over long periods, is that I can ask what the ensemble average is between a noise component at one frequency and the noise component at a slightly displaced frequency in the signal. And I ask what that average is over time or over the population. And if you go through, once again, the arithmetic, subject to a function that has a limiting behavior for sufficiently large epochs of time, such as we will be dealing with, it approaches a delta function. What you conclude is that this function is the power spectral density if f is equal to f prime, but that different frequency bins are orthogonal to each other. And this is useful in many of the derivations that allow you to further simplify the analytic derivations that are used. But that independence in frequency bin, which allows us to estimate statistics, is based on the fact that the noise properties do not exhibit transient behavior. In other words, this is not a function of time. As soon as you have any kind of time dependence in the noise process, then you destroy this independence of frequency bins. And the typical limiting case, for example, is if you have a white noise spectrum, that could, if you don't know anything about the phase, that could either be a hiss or it could be a clap. A clap is the case in which all the frequency components are exactly in phase so that they add up to a delta function at one period in time. But if you have statistically independent frequency components of the spectrum, that corresponds to white noise hiss, as we call it. And so this power spectrum by itself doesn't tell you all the information. You need to know about the phase coherence between the bins and whether you have white noise or a very sharp clap. So we have this instrument. We have a bunch of electronics up front that are cleverly designed to produce the best representation in digitized signal of what this instrument is measuring in terms of strain. And one thing we do immediately is we capture that on tapes at the full bandwidth. So we have an archive that we build here at Caltech, which provides a historical ability to look back at any of the previous data that are acquired by the instrument. At the same time, what we will want to do is generate our best estimate of what h of t is from the raw data that are being acquired by the instrument. And the first thing we want to do is consider a series of pre-processing and conditioning steps that will be done in the analyses that we will do on the data. One thing, for example, is if we lose lock, we produce a gap in the data, but for many analyses, you don't want to just stop the analysis and start again, so you have to come up with, it's not unique, and you just come up with the best way by which you can fill in the gap, so to speak, in data dropouts to allow an analysis to continue seamlessly through instrumental periods of dropout. And then later on, you zero out events that may have occurred during that epoch because you know when it dropped out, and so you can use a veto at the end of the analysis. We have to calibrate because what we measure is ADC counts, which comes from a digitization of a voltage, and what we really want to know is strain. And each of those involve rather complicated transfer functions of this instrument as a transducer, and that calibration takes place at this point in the analysis chain. If we have competing signals from other channels that we know exist, it's conceivable that if we have adequate signal to noise, we can produce a better representation of the fundamental channel h of t by subtracting out coherently, either in the frequency domain or the time domain, the contribution and contamination produced by signals that have measurability into the process. And that involves, for example, we invariably will have evidence of the 60 hertz power mains present in many of our data. Those of you who've seen LIGO spectra are well aware that there are all these lines in it. But the lines are very high signal-to-noise features that, in principle, if we had a way to understand what was added to the signal to produce that, one could subtract that coherently to produce a better representation of white noise that goes into the analysis chain. And then one thing is, since we have such a huge data volume, we want to consider a case in which we want to decimate and reduce the data sets so that for many analyses we don't need 16 kilohertz per kilosamples per second acquisition, and consequently it makes the computing job more tractable if you have fewer channels. Just to remind you briefly, this is data from the 40 meter of several years ago. If this is what nominal behavior is, then oftentimes, depending on what happens, if you have mode hopping due to angular fluctuations, you get these transient bursts that clearly represent non-stationary noise. You also get this, if the system is oscillating and ringing due to the normal modes of the system, it is often the case that you get beat patterns that have to be taken out or accommodated in the data analysis. And then every time the system is brought into lock, the servos introduce energy into the system that causes the system to ring, and you get a classic period of time during which you have to basically dismiss the data because it's too noisy, and then you wait and then start looking at the data after that period. This represents an excerpt from a paper, GRQC, that Bruce Allen, Hua, and Adrian Ottawil produced back in '99, where they took a look at several channels and asked the question, is there, by looking at the cross spectrum that we talked about earlier, and then looking at the magnitude of the response function between channel A and channel B, where A is the gravity wave channel, you come up with a metric by which you can say the degree to which this signal is affected by channel B, where B, in this case, represented any one of 10 channels. By suitably averaging the data that you acquire over a period of time, you can deduce the matrix then that corresponds to how you would subtract out the channel J not equal to A from the signal to produce a better estimate of A, such that this signal is perpendicular or orthogonal in the frequency domain to all other signals. And then if the arithmetic is such that this matrix corresponds to the inverse of the matrix that corresponds to the transfer function of all these channels, with a numerator that's the particular value of the index of that element of the matrix corresponding to the channel Ka. And it's basically a generalization of a two-dimensional coherence function, which is the power in the product AB normalized by the respective powers in A and B separately, which is a function that goes between -1 and +1. And in this particular example that was quoted in the paper, you go from a channel for which you just basically have a lot of contaminated signal to one that has an RMS that's approximately something like a factor of 2 less, and allows you to detect a glitch which wasn't obvious in the original data. If you ask how much computational power does it take to do such a regression analysis on the fly for our channels, the answer is that even if you can conceive of understanding to the degree you need to do a very good job of removing the cross-contamination from many channels, such as, let's say, 64, it is possible to do that on a single CPU machine. It's a relatively inexpensive calculation. So we have, in our design, we have a machine up front that does the signal processing that will be used to produce a cleaner estimate of H from the raw data before we feed it into the pipeline analyses that correspond to the astrophysical filters.
Do you have any understanding at this point of how much you're actually going to buy with this, whether you're going to buy anything?
The E7 data were too transient to allow this kind of analysis, and so it's still in the future for LIGO 1. LIGO 2, I mean, the 1994 data, one could buy something like a factor of 2 to 3 improvement in RMS, but the corresponding improvement in, let's say, the limiting noise that was quoted in the 1994 paper that came out in '99, that analysis was never done. So the end-to-end improvement is still an issue, and clearly if it's vanishingly small, you don't want to invest the time in it. But we want to make sure that we have the ability to do it if we decide that we want to. One reason that's of interest is most of our data are whitened because you can't accommodate in the digitization domain the very large excursions between the seismic limit at one end and the sensitivity in the middle. And much of the dynamic range is then eaten up by these lines that occur, because even if you have a white spectrum, it's a cone with these many lines on top. And so one wants to consider a situation in which we might be able to compress the data further for archival if we suitably clean it up. So I was going to now digress or continue into discussing the time frequency analysis of data. Up to now we've talked about individual channels or a few channels. But if I consider a very long time series, another thing that I can ask in order to assess whether the series consists of stationary noise is to break it up into small chunks and then turn each of these chunks on their sides and create a carpet or tapestry in which the vertical axis is the amplitude of the signal and the horizontal axis corresponds to epoch of time during which that spectrum was collected. This allows us to assess what dynamically changing time series information may be present in the data, and it creates an image of the dynamics of the system that are not immediately obvious certainly to the human eye if you simply look at a one-dimensional time series. And the method by which you get there is not unique, but they do derive, the time frequency images all derive from a common generalized frequency transform. And what I took here from one of the papers that I'll mention as a reference in the next slide, the original formulation actually occurred by Eugene Wigner back in 1932, where it was used in quantum mechanics, where the kernel then had to do with the wave function evaluated at two different points in time and then Fourier transform. As I said, there's a unified representation of the frequency time transform, P of t and frequency, which is a three-dimensional integral over time and two other frequency components that are integrated out. And you look at the spectrum of the signal at 2 points, at two frequencies, multiplied by an integration kernel. And if the kernel's unity, then you get the Wigner function. And over years, for various different signal processing applications, different kernels have been applied. The one that we use and have been using currently is a spectrogram, which is basically H is a window function. So this is the integral that functionally does what I do here, which is I only collect data over progressively shifted windows of data. And that produces a map of the power spectrum as a function of time. I show here before we go into, I'm sorry?
I need to change it.
Oh, okay. I need a glass of water. Oh, is there a fountain outside? Yeah.